Hello, class. Welcome to chapter 5.5, 5.7. Today we're going to be talking about doing free body diagrams and equilibrium in 3 dimensions. We're going to be talking also about constraints and static determinacy, not statistical, static determinacy. So, summary for today, we're going to look at what it is to be statically indeterminate. We're going to talk about the idea of improper constraints, and we're going to get into 3-dimensional supports, which look a lot the same, but there's a couple new types of supports that we see in 3D that we didn't see in 2 dimensions. So our additional 3D supports, there's just 5. And the reality is some of them are actually repetitions. These journal bearings and thrust bearings, these look a lot the same. So we've got ball and socket, we've got a hinge, which you've been seeing your entire life, and we've got journal bearings, which are fairly new. The other 5 new supports actually look a lot like their 2-dimensional counterparts, just you add an extra dimension. So our first one is a ball and socket. This might look familiar to you. This is a pretty common detail on cherry legs. So they'll sit no matter what sort of ground they're set on. You have a nice even surface. You've got 3 components, FX, FC, and FY. If you think about this, here's kind of an example off a piece of construction equipment. This ball is kind of captured by this bolted connection. This ball and socket joint actually looks a lot similar to joints in your own body. This is the way our shoulder joints and our hip joints work, right? You've got a ball and socket. This might be your femur coming into your hip bone. The other type of connection we'll see a lot are journal bearings. Journal bearings are used a lot in vehicle applications. If you've ever thought about the way your engine is connected, you think about the pistons in your vehicle that move up and down. You've got a piston that's connected via a rod to our camshaft, our crankshaft, which looks something like this. Kind of a jaggedy looking rod that rotates, and that crank rod or crankshaft is what translates that vertical motion of your piston up and down into a rotational motion, but holding that in are these journal bearings that look kind of like this. You can think of this as your piston rod here. So you want that to be able to freely rotate, but maybe you don't want it to rotate in the Z-axis. We don't want this thing to wobble. And we don't want this to rotate in the X-axis because that would also create wobble in a different direction. And this thing has a little give back and forth. Another type of bearing that you might see is called a journal bearing with a square shaft. When we have a square shaft, we have this problem of, hey, you've got a square instead of a nice circular shaft. This means that this thing is not going to rotate about that. We have an additional constraint in the moment about that y-axis, that longitudinal axis. So this thing can't rotate. We still have a little bit of movement in and out, so you can see that it's not constrained in the force. There's no force in the y direction, but it is constrained about rotating about that axis. And our final bearing, which is it looks a lot similar to our journal bearing. If you look at this, this looks almost exactly the same. If I look at the pictures of the two, a journal bearing versus a thrust bearing, they actually look almost exactly the same. You have to look very closely over here at the restraints to get an idea of the difference between these two, so be careful when you read these problems. Don't just look at the pictures, but also read the text carefully to make sure that you're not trying to use a journal bearing versus a thrust bearing. Make sure that you read that text very carefully because it'll tell you the type of connection often there. In this case, we have Fy, which says, hey, this pin cannot move, slide back and forth in its socket, in its bearing. And this is a very similar example of what you might see in real life. This comes off a piece of construction equipment. Here is a thrust bearing. And if you look at this, if I tried to pull this out, I try to apply a force in the Y direction, right? This is not going to move. I have a restraint here that's going to keep this from pulling out. So typically what you'll see in a crankshaft is a combination of journal bearings, and then maybe at the end they'll have a thrust bearing that holds it all in place and keeps that crankshaft from just sliding right out. We might have a thrust bearing right there, and you might have normal journal bearings kind of spread out along the length of the engine to kind of just provide some additional support to keep this thing from vibrating quite as much. And our last connection, the simplest connection of all, one that you see every day, every time you open a door, is a hinge. This is pretty common, right? And in this case, this is constrained such that there's only one free direction of rotation. That's about the axis of the hinge, which is, in this case, they've defined this as Y, so that's going to be moment, or about the rotation about the Y is the only free direction. So let's just go ahead and add a color here and say, hey, this is rotating freely here. Rotates freely there. All right, so those are all the new connections. And hey, after we draw our connections, we get our free body diagram drawn. The next step is applying our equations of equilibrium. In 3 dimensions, we can use the vector math if we want to, right? That doesn't look any different. Sum of all forces in the F vectorially equals 0. All forces, all moments about some point O equals the null vector or 0 vector, hey. And if we go to scalar, well, the scalar is where it gets kind of cool, because when we break it down scalarly, we actually create not just one extra force, but we get a lot of extra moments. And a lot of students look at this and go, oh my gosh, oh, this is terrifying. Now I've got all these equations to choose from. But in reality, what you've done is now you've gone and created a lot of extra equations, which means we can solve for more unknowns. We've just expanded our repertoire, as it were. We can now solve for a lot more complicated and a lot more interesting problems, honestly. So now we went from 2 dimensions. In 2D, we had 3 equations. In 3D, we have 6, which is really awesome. We can now solve for a lot more complicated and more interesting structures. Now, when we solve for systems of equations, right, we have to have a number of unknowns that's less than or equal to, let me make that change here, less than or equal to the number of equations. In 2 dimensions, we have 3. In this example, let's think about this example for a little bit. If I drew a free body diagram of this, let me change my color here real fast. Let's go to a black here, and we'll draw our shape. Let's draw our equations. So here we have a roller at C. You've got a roller here at B. Here we have a moment connection at A. You've got AY. We have AX. We've got an applied force here. And we've got a couple moment there. In this case, we have 1, 2, 3, 4, 5 unknowns. We have 5 unknowns. We have 3 equations. We can't actually solve this using statics, right? And if we think about this, we could actually probably remove one of these supports and reach equilibrium. If we got rid of B, hey, that would stand on its own, or we could get rid of A and keep B. Either one of those cases, we'd have a system that would be still stable, right? This could be statically stable, it wouldn't move. In this case, we call those extra constraints, we call those redundant, right? It's this idea that those extra constraints, they're redundancy, they're not actually needed. And since we don't have enough equations, we actually can't solve this particular system. This is what we call statically indeterminate, which means, hey, we can't solve it with the statics tools we have. We're going to have to use another system of analyzing this. It doesn't mean that we can't do it at all. We'll get into later how to model this in terms of stiffness and how to solve for forces, internal forces using that. But that's a topic for Engineering 225. So if you're interested in solving kind of these more complex situations, register for that class. Also, just a reminder that registration opened yesterday, so make sure you get on it right away. All right, so our other case, kind of the opposite end of the spectrum from having redundant constraints, is this idea of having improper constraints. This is saying, hey, we're actually not constrained in one of our degrees of freedom. This could be either, when we're talking about degrees of freedom, that could be a force direction, or it could also be a moment axis. Thinking about this particular problem, when I apply this force P here, since this is a roller, I really only have a force in the x direction. There's nothing to keep this thing from just rotating until it falls down. That's just going to fall down. When this falls down, hey, this is improperly constrained. Very simple example. All right, so for the CA for today, we're going to mix it up a little bit. I'm going to stop the recording here for a sec and ask for questions.